Yay!
Yay! Okay, here's another common sort of a problem that you'll find in rotational dynamics, and that is, suppose I've got a bucket, maybe my little m, and it's wrapped around a cylinder, and I just let the thing fall. And so let's say that this thing is going to fall 10 meters into the water below, let's say. So my bucket weighs 15 kilograms, and it's wound around a cylinder, solid cylinder of mass of 12, radius of 15 centimeters. And what I want to know is, what is the acceleration down of that bucket? It's not going to be free falling, because it takes some effort to start spinning up that cylinder, right? It's going to sort of retard the motion a little bit. So I wouldn't expect it to be moving down at 9.81 meters per second squared. It should be a little bit less than that. So let's figure out how much less than that. What is the rate of fall going to be? So what we do is, kind of similar to the last problem that we did, we're just going to set up Newton's laws for the mass, and we'll include the torque on the cylinder. All right, so here we go. So the forces on the mass, let's see. I got tension going up. So T minus mg is just going to be minus ma. Right? Minus because the acceleration is in the down direction, and I called the tension up to be positive, so I've got to be careful of my signs. All right. And then what else do I know? So that's the equations for the mass. This is for, I guess we already called it a bucket. And for the pulley, what do I know? I know that tension is going to be acting at a distance r away from the center of the pulley, right? So it's going to exert a torque TR. So that torque, TR, is going to be equal to I times alpha, right? And so I is going to be 1/2 mr squared. It's a solid cylinder. And then alpha, if it unwinds without the rope slipping, then the relationship between alpha and just regular A looks like that. It's just A over R. So once again, I can bring this R over to this side, and it cancels all those R's. So what this tells me is that the tension on the rope is just 1/2 m times A. Very cool. So now I can substitute that back in above and solve for A. So this means that 1/2 ma minus mg equals minus ma. Okay, so A times 1/2 big M plus little m equals little m times g. So my acceleration is mg over 1/2 big M plus little m. Okay, neat. So if I plug my numbers in, what I get is about 7 meters per second squared, right? And that kind of makes sense. I mean, at least it makes sense that it's less than 9.81 because it's not free falling. There's some resistance to it falling freely, and that is because it's got to unwind. It's got to start that a pulley, that drum spinning up there. And if you want, you can go back and figure out what the tension in the string actually is. So now you can go back and plug the numbers up at the top, and what you'll get is like 42 newtons. So you can find the tension in the rope as it falls, which is another sort of a classic problem. You can also ask, how long will it take for it to hit the bottom? Because that force is going to be constant as it falls. So how much time? Until it hits the water. Well, now we can go all the way back to our kinematics, right? Really, really early in our study of physics. And we can say like delta y, the height that it goes, the change in the y position. Let's just call that down being positive just for kicks. And so this is just going to be 1/2 a t squared. So the amount of time it's going to take is just going to be the square root of 2y over a. There we go. And so if you plug these in, what you're going to get is, what did I get? 1.7 seconds. How fast will it be going when it hits the water? V is AT if the acceleration is constant. And so if you multiply those together, what you get is like, what did I get? 11.8 meters per second. Very cool. So that's how fast the bucket is going to be going when it hits the water. Okay, so taking into account freely falling objects as they sort of unwind and start to spin a drum or a pulley up top, all that stuff is fairly easy to take care of. Cool.